All right, so this is question 17.30, straight out of the textbook. Good question, and this is one of the most challenging things in this chapter. So this is question 17.30 from Klein, 4th edition, and we're going to start with A. And the question just asks you, is this an aromatic compound, an anti-aromatic compound, or a non-aromatic compound? So we'll just use A, double A, and Na. Okay, so let's take a look at the first one. So the first one they gave us is something like this. We have a 6-membered ring, then it's conjugated to this bond. Oops, I can draw that a little prettier. And then we have a lone pair over here. Would this be aromatic, non-aromatic, or anti-aromatic? Well, remember the criteria is that we have to have a continuously overlapping system of p orbitals. And we know that this lone pair is in a p orbital. And how do we know that? Because it's participating in resonance. How do I know that? I could draw a resonance structure like this. So the lone pair is definitely in a p orbital. And I'll just take the time to draw this resonance structure the best I can, like this. So we know, and again, we could draw more resonance structures, but that's just one example of a resonance structure. So again, we know that that lone pair of that carbanion, just going to put etc. over here. We know it is participating in resonance, therefore it is in a p orbital. So every one of these carbons that I'm highlighting, and that's every dang carbon in here, is sp2 hybridized. And now we just need to ask ourselves, all those electrons that are in those p orbitals, do we have a Huckel number or not? Okay, because if we don't, then it's going to be anti-aromatic. And if we do, it's aromatic. Well, how many total electrons do we have? We have 4 double bonds. So that's 4 times 2. So that gives us 8 electrons plus the 2 here. So we have a total of 10 electrons. Is that a Huckel number? Can anybody tell me, is 10 electrons, is that a Huckel number? I'm sure somebody's got it memorized by now. Yes. Yeah, absolutely. You're all 100% correct. So it's 4n plus 2 when n is equal to 2. You take 4 times 2 plus 2, and that gives you 10. And therefore, this is aromatic. I said I was just going to use the letter A in a circle, didn't I? Okay, so we'll just put an A. Anarchy symbol, kind of. Okay, any questions about that one? Well, I won't keep saying that. If you have a question, just stop me, okay? So that one's aromatic. The next, go ahead.
So I'm kind of confused about this still. So I don't see how, like you said, it's 4n plus 2 electrons, but also it doesn't have to be an even number of electron pairs.
No, it's an odd number of electron pairs.
Oh, okay.
Right, so it's 4n plus 2. So Caitlin, get this straight. 4n plus 2 electrons in the p orbitals. So let's see here. If we have 4n plus 2, this is, let's do it like this. Total, we'll do total electrons is going to be 4n plus 2. So we'll put that over here. And then we'll do electron pairs. So if we have n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, something like this. So what's 4n plus 2? So let's see here. If we have 4n plus 2 and n is equal to 0, then we have 2. 2 divided by 2 gives me 1. 1 is an odd number, so you have 1 pair of electrons. If you have n is equal to 1, then you have 6 total electrons. 6 total electrons in p orbitals. 6 divided by 2 gives me 3 pairs. 3 is an odd number. If you go to 2, 4n plus 2, so that gives you 10. 10 divided by 2, so that gives me 5 electron pairs. If you have 3, then you have 14 total electrons in the system of continuously overlapping p orbitals, and then you divide that in 2, and you have 7 pairs. So the number of pairs of electrons is always an odd number, odd for the Huckel number. But the total number of electrons is always an even number. Does that help?
Yes. Okay, that makes sense.
Thank you. Cool. Cool. Yeah, it's just something you got to get straight in your mind. It's all good. Let's try B. So this is 17.30 B. This compound is called thiophene. So thiophene, There we go. Like that. So is this an aromatic compound? Yes or no? Well, the question kind of is, what's the hybridization of this sulfur here? Right? We know that an aromatic compound is more stable than a non-aromatic compound. That was the whole point of looking at a closed shell electron configuration. And if we count up the total number of pi electrons in the double bonds, we have 1, 2, 3, 4. But if we were to put 2 of these electrons, or one of the lone pairs, into a p orbital, if this sulfur is sp2 hybridized, then we have a continuously overlapping system of p orbitals, and we have 2, 4, 6, or an even number of electron pairs, or I should say a Huckel number of electron pairs would be more correct. Okay, so we have a Huckel number. We have 4n plus 2, where n is equal to 1. So it's a Huckel number. We have a continuously overlapping system of p orbitals. So what's the compound? Could anybody answer me? And I'm not trying to fool you or anything or embarrass anybody. The answer, I'm hoping, is kind of obvious. Go ahead.
Aromatic.
Hot diggity darn. Absolutely. It's just a plain old aromatic compound. Aromatic. Yeah. So we'll put our A here. What's next? Next one's kind of a neat looking compound. I don't know if I've ever used a compound like this before. I've used naphthalene and derivatives of it, but not anything like this. It's kind of like you've got a naphthalene, and then you've got this bridge going over it like this. However, if you look at the carbons in the 2 fused 6-membered rings, we have 1, 2, 3. Every one of these carbons that I'm highlighting in yellow is sp2 hybridized. There's no arguing any of that. Now, these 2 carbons over here are sp3, but there's no pi bond there. So we really only need to focus on the system that has the pi electrons in it. And is that system aromatic? Well, if we count up the total number of pi electrons, we have 2, 4, 6, 8, 10. So we have 4n. We have 4n. Son of a gun. 4n plus 2, where n is equal to 2. And so since we have a continuously overlapping system of p orbitals in this bicyclic system here, then this would be aromatic. Call this an aromatic system. Now this ring over here is non-aromatic, but the portion that I have all the yellow carbons highlighted in, it is aromatic, right? And it would be akin to saying, well, is toluene aromatic? Because you have benzene, you have an aromatic compound, but then you have an sp3 hybridized carbon coming off it. Well, that's neither here nor there. The compound itself is still aromatic. And the same thing here. If you have just plain old naphthalene, and we looked at naphthalene when we looked at phenanthrene and that kind of thing. So if you look at this compound, this is naphthalene. It is an aromatic compound. And if it was to have, let's say, a methyl group here and a methyl group here, that doesn't change anything. It's still an aromatic compound. So the compound in C is an aromatic compound. Let's try D. This is another good one. This is 17.30D. What is this? We got something that looks like this. And I'm just going to throw this out there to my students without any aid, without any assistance. Could anybody tell me, would this be aromatic, non-aromatic, or anti-aromatic? Anybody have an idea about this one?
I have a question.
Yeah, go ahead.
About this. So I'm getting a little bit confused between, like, I know in lecture you kind of said that, like, obviously if a compound can be aromatic, it wants to be aromatic, and it'll choose that. But I'm getting a little bit confused when I look through the examples in the book, because sometimes there's opportunities for a compound to be aromatic, but it doesn't choose that. And it's anti-aromatic instead, and that's confusing to try and get that straight in my mind.
That can't be. That would be impossible, because there's no way a compound could choose to be one or the other. Because if a compound is aromatic, it's going to satisfy the Huckel number, 4n plus 2, whereas if a compound is anti-aromatic, it's going to satisfy 4n. So there's no way it could be one or the other. It's got to, or it could decide to be one or the other. It could go from being non-aromatic, okay, or for being something that you might presume is non-aromatic. Like if we go back to thiophene, we go back to this example here, if this sulfur was sp3 hybridized, then the compound would be non-aromatic because it wouldn't have a continuously overlapping system of p orbitals. But there's nothing it could do to be anti-aromatic. That would be impossible. So does that make sense?
Can I follow up with another clarifying question then?
Go ahead.
So I was trying to go through some of the problems, and I think that it's actually in these string of problems. There's one where it's got like two nitrogens on it, and one of them's connected with a hydrogen, and you know it's the same like parameters for the question, asking anti-aromatic or non.
So something like maybe like this. So
yep.
So something like this.
Yep.
So this is imidazole. Imidazole is a very common aromatic or common ring that's found in aromatic compounds. So if you look at this compound, right, you have 4 pi electrons in the double bond, and then we have this lone pair which is not participating in aromaticity. That pair is localized. So that's something that we went over in Organic Chemistry 1, why that is localized, because the nitrogen, this nitrogen has 3 regions of electron density around it. It's got a double bond, a single bond, and a lone pair. Therefore, it must be sp2 hybridized, sp2, but it already has a pi bond in it. And so there is a p orbital that has an electron, right, that's overlapping with this p orbital over here. So therefore, this lone pair is in an sp2 orbital. It is not in a p orbital. So we have 1, 2, 3, 4. And if we had this lone pair in a p orbital, then we'd have a total of 6 electrons. We'd have a completely overlapping system of p orbitals. So we would satisfy the criteria for a compound being aromatic. And so this would be an aromatic compound. Why? Because this nitrogen is sp2 hybridized. Does that help a little bit?
Yeah, no, that does. Thank you.
Right. If you go back to something like ammonia, well, if you look at the nitrogen in ammonia, right, just plain old NH3, that nitrogen is sp3 hybridized. But something that you got to remember, and this goes all the way back to Organic Chemistry 1, so it would be somewhere around section 2.12 and 2.13, that whenever a lone pair participates in resonance, it's going to occupy a p orbital rather than a hybridized orbital. All right, and that's something that we saw with the cyclopentenyl anion when we looked at its aromaticity. So if we go to this compound here, you can see that this compound is non-aromatic. Why would that be? Because this carbon is attached to 1, 2, 3, 4 carbons. This is an sp3 hybridized carbon. There is nothing you can do to change that. It's got no lone pair on it. There's nothing you can do about it. So we do not have a continuously overlapping system of p orbitals. Therefore, if the first criteria isn't fulfilled, this is a non-aromatic compound. Let's try another one. We already did tropylium, so let's see here. Let me just ask you here. Let's try a couple other interesting ones. Then we'll have to move on to chapter 18. But this is from question 17.32. There was a couple of good ones. So look, I'll just review with you quickly. If you have 2 fused rings like this, and we've already looked at this a few minutes ago, this compound, this is naphthalene, it is aromatic. If you break this bridge here and you make 10 aniline, so that's a 10-membered ring. If you count the total number of carbons in here, you have 10 carbons. And if you conjugate the whole thing, you might say, well, hold on. This is aromatic because I have a Huckel number, 10 total electrons. I have a completely overlapping system of p orbitals. Therefore, this is an aromatic compound. But this compound is not aromatic. Can anybody tell me why? Something that we went over in class. This compound is actually non-aromatic. And there's a reason. No, go ahead.
Other compound, so it's not planar.
Exactly. It's because the ring is actually so small, and you've got a hydrogen coming off here, and you've got another hydrogen coming off here. You can see it was even hard for me to draw those. And because of those two hydrogens, it pushes the ring out of planarity. And since you don't have, since it's not planar, you can't have that overlapping system of p orbitals, and that renders it non-aromatic. You've got to have all of those p orbitals overlapping. It has to have a conduit. It's the same rationale that when we looked at, cyclobutadiene, we said that this is anti-aromatic. There's nothing it can do. You've got a fully conjugated system, overlapping system of p orbitals, but you've got 4n electrons where n is equal to 1. So this is anti-aromatic. Whereas when we looked at, that's not a very good straight line. So when we looked at cyclooctatetraene, this molecule right here, you might think, well, this is anti-aromatic too. I've got a closed system. I've got a full system of overlapping p orbitals, and it's got a Huckel 4n number, 4n where n is equal to 2. So therefore, this is anti-aromatic. And I said this is a specific case. This compound is not anti-aromatic because it adopts the tub shape. Now, please forgive me. I'm going to try to draw the tub the best I can, but it adopts this shape here. So what it does is it prevents orbital overlap. So you end up with very isolated pi bonds. I'm not going to draw the entire thing, but the tub shape prevents the orbital overlap of all those p orbitals, and thus you don't have a continuously overlapping system of p orbitals. Thus, it's not anti-aromatic. It just becomes non-aromatic. Why don't we look at one more example that I think is a good one? Go ahead.
So how are we supposed to be able to look at some compound like that and know, like, for example, that it adopts the tub shape?
Memorize this example.
Okay, so we should just learn.
I would memorize cyclooctatetraene. Yes. Very important example. Yep. All right, let's try one more, and then we'll move on. Let's see. 17.32C is kind of a neat one. 7.32C. You've got this interesting ring here. You've got 3 oxygens in a row, 3 oxygens and 3 lone pairs, like that. So let's see here. Is this aromatic, anti-aromatic, or non-aromatic? Well, let me guide you through this. Okay, so if any of these oxygens can adopt sp2 hybridization that would cause the compound to become aromatic, they'll do it, won't they? Okay, well, let's ask ourselves. If we were to put a p orbital here, let's imagine we made this oxygen. What's wrong with my Apple Pencil? Let's imagine we made this oxygen sp2 hybridized. Then you would have 1, 2, 3, 4. Oh, shoot, that's not good. That's 4n. So that would be anti-aromatic, but that would still be non-aromatic because you don't have a continuously overlapping system of p orbitals. So let's imagine that we make a Huckel number. Let's put a p orbital on here. Let's make this oxygen sp2 hybridized. Now you've got 1, 2, 3, 4, 5, 6. You have p orbitals, but you don't have a continuously overlapping system, do you? No. If this oxygen is sp3, then this compound is non-aromatic. Now, if you're saying, well, put a p orbital on there, man, just do that, then you'll fix the whole thing. Okay, let's try it. If we put a p orbital on here, and we put a pair of electrons in it, then we do have a continuously overlapping system of p orbitals. But how many total electrons do we have in there? 1, 2, 3, 4, 5, 6, 7, 8. That would be anti-aromatic, and we don't want to be anti-aromatic. And thus, one of those oxygens is going to be sp3 hybridized, and so the compound is non-aromatic. All right, and so this is a non-aromatic compound. Again, if every one of those oxygens had a lone pair and a p orbital, then it would be anti-aromatic. So one of the oxygens has to be sp3, which renders the compound non-aromatic. You know, I was looking at some of my notes that I had made a while ago, and I was thinking, you know, how many anti-aromatic compounds are there? There are actually very few anti-aromatic compounds out there. So we're talking about anti-aromatics. I went to go talk to one of my colleagues one day about anti-aromatic compounds, and I was asking him about, you know, what about this and what about this? And he said, well, this has never been made. You know, it's never even been isolated. I think the two most important ones that we learned were cyclobutadiene is anti-aromatic, and the cyclopentadiene cation, we said that it is anti-aromatic. Another one that doesn't come up in our textbook, I'll just draw it for you, is this is called Pentylene. So Pentylene, and again, it's not even in our textbook, so I wouldn't stress about it a whole lot. But here you have a continuously overlapping system of p orbitals, and you have a 4n where n is equal to 2. You have a total of 8 pi electrons. Other funny things that are anti-aromatic are, let's say you had an oxirane like this, but then you had a double bond in here, right? This lone pair can participate in resonance, so it's in a p orbital. However, you've got a continuously overlapping system of p orbitals, but you would have 1, 2, 3, 4, which is 4n, where n is equal to 1. So that would be anti-aromatic. Another example would be the same thing with a nitrogen in the ring, like this. And so that would be highly unstable. Same thing if you had a cyclopropenyl anion, that would be anti-aromatic as well. Let's see, there's other like little funny ones. Biphenylene. So if you have a compound that looks like this, biphenylene, and again, I wouldn't stress about biphenylene a whole hell of a lot, pardon my language, but biphenylene looks kind of like this. So you do have a continuously overlapping system of p orbitals, and you have 12 total pi electrons, so that's for n where n is equal to 3, so that would be anti-aromatic. And then you remember how we saw the tropylium ion, the tropylium cation was aromatic, so that's this guy here. Well, if you were to put a lone pair in there, right, this could participate in resonance like that. So that means it is in a p orbital, but then you'd have 8 pi electrons, and so that would be oops, did I erase all that? Well, it's a good thing the video recorded it, or at least I hope it did. Oh, here we are. So this would be anti-aromatic as well. Let me just fix that up like that. So these are anti-aromatics that I came up with. And again, many of these compounds haven't even been isolated, but these are some examples of anti-aromatic compounds. There we go.